Hi, I'm Rezvan. I'm going to be talking about cortical parcellations that are adaptive to the limitations of the spatial resolution of the EEG image data, which might prove useful for the whole brain connectivity analysis in the source space. I'm going to start by briefly talking about the spatial resolution of the EEG image and how to quantify it. Then I'm going to carry on by talking about a couple of algorithms that we've been working on in order to obtain adaptive parcellations of the cortex. And finally, I'm going to show you, based on some simulated networks, how the performance of the adaptive parcellation would compare to that of the anatomical parcellations. Right, so with the EEG image data, if we want to look at the whole brain networks, we typically start by parcellating the cortex, then we extract the RI time courses, and finally find RI by RI connectivity matrix. But the first step would be to parcellate the cortex, and most studies use anatomical parcellations for this purpose. For example, these parcellations have been very often used in the literature. But the question is, are these anatomical parcellations optimal? Because with the EEG image data, we know that we're recording signals from outside the brain, typically starting from less than 400 sensors, and we would like to estimate several thousand sources of activity in the brain. Therefore, the problem is called ill-posed, and we can't really mathematically solve it. Therefore, even though we have a very good time resolution, our spatial resolution is going to be limited, meaning that we might lose sensitivity or specificity of the data. But is there any way that we can actually quantify these problems? Some studies have introduced crosstalk functions that can be used for this purpose. And what crosstalk functions are going to tell us is, if we are interested in this blue source over here, how much is it going to be affected by the signal coming from itself as compared to the leakage of activity from the surrounding areas? And we can use the crosstalk functions to look at the sensitivity problem. For example, here, if we look at the supramarginal gyrus and look at the crosstalk function for this area, we see that there's quite nice overlap between the two. While if we look at the insula, which is deeper in the brain, it is more likely to receive leakage of activity from the anterior temporal lobe as compared to itself. We can also look at the crosstalk functions to look at the specificity problem. For example, if we have RIs that are too large, they might produce several distinguishable patterns of CTF, several distinguishable peaks of CTFs. Or if we have RIs that are too small or too close to each other, they might produce highly overlapping patterns of CTFs that are not distinguishable. So our purpose would be to obtain adaptive parcellations for the EEG image data by identifying as many distinguishable RIs in the brain as possible. And from what I showed you in the previous slide, we can use the CTFs to identify and remove the RIs with low sensitivity, merge the RIs that show highly overlapping patterns of CTFs, split the RIs that produce distinguishable patterns of CTFs, and finally, for each of the RIs, identify a set of representative vertices that show that are highly sensitive and specific to that particular RI as compared to the rest of the RIs in the brain. Right, so taking these into account, we have worked on a couple of algorithms. In the first one, the split and merge algorithm, we start from anatomical parcellations and when we modify them based on the crosstalk functions. For example, here we started from districts atlas. We find the CTFs for each of the RIs, and for each RI, we identify how many principal components are required to explain more than 90% of the variance of its crosstalk function. And if we required more than one principal component, we will split that RI into several RIs. Then we obtained a set of split parcels. Based on these split parcels, we found the crosstalk functions, and we applied a Z-score criterion, and what this Z-score criterion is going to tell us is that for every vertex in the brain, how sensitive it is to each RI as compared to the rest of the RIs in the brain. Based on this Z-score, we identified three sets of vertices. Decline vertices were the vertices that were insensitive to all of the RIs in the brain. Assigned vertices were the vertices that were highly sensitive to one and only one RI. And we had a third set of vertices where they were highly sensitive to more than one RI. We clustered those together and obtained a set of merged vertices. We put them together with the split parcels and applied the same Z-score criterion and obtained a final parcellation based on the split and merge algorithm. Right, so we started with the split and merge algorithm. We started from anatomical parcellation, but in some studies we might just be interested in obtaining as many distinguishable RIs in the brain as possible with no prior parcellation. And so we worked on a second algorithm, the region growing, where we started from all the brain vertices and created RIs from scratch. And what we did was that we identified a set of seed vertices which were the vertices that produced the strongest patterns of CTFs in the brain. We grew regions around them, and we obtained a set of RIs in the brain. Then we applied the same split and merge criterion. We obtained a final set of RIs. Right, so now that we have this final parcellation, what is the performance of them? At first step, we evaluated the performance in theory and using something called RI resolution matrix. And what it tells us, it's an RI by RI matrix. And the diagonal elements show how much each RI is receiving crosstalk and leakage from itself, and the off-diagonal shows how much it's receiving leakage from the rest of the brain. So ideally, we want it to be an identity matrix, and based on this matrix, we define two indices, the sensitivity and distinguishability indices. The sensitivity is the average of the diagonal elements, and the specificity is the correlation between the RMAT and an ideal identity matrix of the same size. When we looked at the RMATs for the anatomical parcellation, it was the sensitivity and distinguishability indices were around 0.4. We managed to improve it to some extent in the modified parcellations, where it was improved to 0.7 sensitivity and 0.65 for this distinguishability. Also, comparing the two final parcellations obtained from the split and merge and region growing algorithms, it shows even though we started from very different starting points, they both ended up to around 70 RIs in the brain, and they obtained the final RIs were highly overlapping. So if we compare here to that, we say that there is high overlap between the final parcellations. And the third point is that both final parcellations are producing a sparse sampling of the cortex. Right, so in theory it seems that it works, but what happens if we apply these parcellations to simulated networks and compare them to the anatomical parcellation? We looked at the performance in two different scenarios. The first scenario, we looked at null networks where we didn't have any true connectivity in the brain, and we wanted to see how many false leakage-induced connections are going to be found with each of the anatomical and modified parcellation. In a second set of simulations, we had actually active nodes with connections between the nodes, and we varied the number and locations of the active nodes, the percentage of connections between them, and the SNR of the data, and we wanted to check how accurate are each of the parcellations in detecting these true networks. Our simulation procedure consisted of three different steps: network construction, reconstruction, and evaluation. During network construction, in order to have no bias in favor of any of the parcellations, we randomly drew active nodes by selecting parcels from functional brain atom atlas, which you might have heard about in yesterday's talks. We defined a connectivity matrix between those active nodes, and we simulated signals in the active nodes and noise everywhere else in the brain. Then, after having this simulated networks, which are completely, the parcellations are completely uninformed about these networks, then we parcellated the cortex using each of the parcellations, extracted RI time courses, and used coherence to find auto connectivity matrix. And finally, in order to evaluate, we identified the significant connections and compared the networks in the presence and absence of leakage, and we calculated the number of true positives and false positives. What we found with the null networks, where we did not expect any true connectivity in the brain, we did not have any true connectivity in the brain, so any connection that we see here is merely due to the leakage. And as you can see, the anatomical parcellation is not performing really great. We have managed to improve it to some extent for the modified parcellations. When we looked at the networks with active nodes and connections between them, I'm just showing an example here. This is the ground truth in the absence of leakage, and this is what we would reconstruct in presence of leakage using each of the parcellations. And when we looked at the true positives and false positives, we found that the true positives are comparable between the anatomical and modified parcellations, while the false positives are significantly less for the modified parcellations. It's also worth noting that the reason we see incomparable TPRs is because if you remember, we had a sparse sampling of the cortex using all the modified parcellations, and therefore, because the active nodes were uninformed about this, we lost around 20% of the nodes and connections just because of this sparse sampling. So the modified parcellations started from a ceiling of 0.8, but however, they managed to have the same true positives as compared to the anatomical parcellations, but with a lot less false positives. It shows that including more RIs, more condensed RIs covering the whole cortex using the anatomical parcellation, it does not help us to have better true positive rates, but it just increases the false positives. Right, so to conclude, I showed that the CTF-informed parcellations, they improve the sensitivity and distinguishability of the RIs, and because CTFs are based on the head, they change based on the head model, inverse solution, measurement configuration, and SNR of the data, the parcellations would adapt to each data set and methods. We also showed that even though we had very different starting points, the final adaptive parcellations, they both ended up with 70 RIs highly overlapping. And also finally, we showed that using modified parcellations can increase the accuracy of network reconstruction, and including more RIs in the anatomical parcellation does not improve the true positives, it just adds to the false positives that we can detect. Okay, I'd like to thank my supervisors, and if you're interested in reading more, we have uploaded the work in the bioarchives, and my poster number is 1790. Thank you.
Thank you so much for the great talk. This floor is open to questions. All right, well, let's thank our speaker again, and thanks to all the speakers of this session for sharing their fantastic work.